we're going to go over 6 different stoichiometry problems. This goes along with the worksheet that's posted online, and we're going to look at 2 just plain old general stoichiometry problems. We'll look at 2 limiting reactant problems, and then finish off with 2% yield problems. Now, we look here, it says several brands of antacid tablets use aluminum hydroxide to neutralize excess acid. Okay, what quantity of HCl in grams can a tablet with 0.750 grams of aluminum hydroxide consume? So we can kind of see that this is our given, and what desired is what quantity in grams. So we want to know how many grams of HCl are in a tablet. Now there is a second question here, and starting with the same given, how many grams of water are in here? So we have 2 problems to do. Here we have our given, okay, the 0.750 grams of aluminum hydroxide, and then we want to change from grams of aluminum hydroxide to moles, and we're just going to use the number that's given here in the problem. Next we have our little heart of the problem, conversion factor, okay, and that comes from the balanced equation. So we see that there are 3 moles of HCl, that's our desired, for every 1 mole of aluminum hydroxide. Finally, we're trying to get to grams of hydrochloric acid, so we're going to use our molar mass, 36.46 grams per mole. And the answer we get for that is 1.05 grams of HCl. That's our first answer. Okay, next we want to look at the same given. So we start the same exact way, but this time we're trying to find the grams of water. So it's exactly the same beginning, okay, grams to moles. Now here's our first difference, and this time here we're doing moles to moles, so we are going from the 1 mole of aluminum hydroxide this time to 3 moles of water, and we go to grams of water, which is 18.02 grams of water, and we get our next answer, which is 0.520 grams of water. So these are 2 very straightforward sort of problems. Next, the equation is given. Okay, what's the maximum mass of iron in grams? So you can see what happens that this is our desired. So desired is grams of iron, Fe, that can be obtained from 454 grams of iron 3 oxide. Well, iron 3 oxide means Fe3+, and we know oxide is O2-, so here we're talking about the compound Fe2O3, one of our original compounds. So we start off with our given, so the 454 grams of iron oxide. Then we can use the molar mass of iron oxide, and since we're trying to get to iron, we're probably going to use the molar mass of iron as well. So here's our conversion factor, 1.59 grams per mole of iron oxide. Heart of the problem, okay, we want to use the 1 in front of the iron oxide and the 2 for the iron. And then finally we use the molar mass of iron to get our answer, 318 grams of iron. Now again, this one has a second problem. What mass of carbon monoxide is required? So that's a new desired. Desired is given is grams of CO. And we're going to start with the same given. So we have the same situation here. The 454 grams of iron oxide, molar mass of iron oxide. And the first change here is when I want to go to carbon monoxide, we're going to use the 3 and the 1 instead of the 2 and the 1. We want the mass of carbon monoxide, that's the 28.01, and we get another answer, 239 grams of carbon monoxide. Okay, now for limiting reactant problems. Limiting reactants are situations where we have 2 different givens. So we're going to have some of this methane and we're also going to have some water. And we have those two givens, and we're trying to find possible yield of H2. So we want to know how many grams of H2. Well, the difference here is we have to find out, well, is it the methane or the water? Which of those two will run out first? So one method, the method I'm using here, is we're going to do two line equations and figure out which one gives us the smaller amount of H2, and the smaller amount of H2 is the real answer. So we start off our given, 995 grams of methane. Then we're going to use molar mass, 16.04 grams per mole. Then we go to the heart of the problem, and we can see that for every 1 mole of methane, we get 3 moles of hydrogen. Then we go for the molar mass of hydrogen, 2.02 grams per mole of hydrogen, and we get our answer 376. Now we don't know if that's the real answer because we have a different compound. We still have our 2,510 grams of water. So we can see what that would come up with. So we start off, same exact beginning, so you have 2,510 grams of water. Now this time we're going to change our grams to moles of water, and our heart of the problem, the bottom, okay, is 1 mole of water because in the balanced equation there's only a 1 in front of here, so we use 1 and 3. But after that, it's exactly the same as the equation before. So when we get all done, we get 844 grams of hydrogen. So we're saying here that this methane is enough methane to make 376 grams of hydrogen, and the water we have is enough to make 844 grams of hydrogen. So this number here is our real answer, and we're going to find out that the methane here is our limiting reactant. It's the one that's going to run out first. So we run them both, two equations using both givens. Whichever gives a smaller answer is the correct answer, and whichever given gave us that smaller answer is the limiting reactant. Another limiting reactant problem, starting with a mixture of 32 grams of sulfur and 71 grams of chlorine, which is a limiting reactant. Also, what mass of S2Cl2 in grams can be produced, so that's our desired. And what mass of excess reactant remains. So we're going to go back and we'll say, let's start with our given. Okay, one of our givens, 32 grams of sulfur. Now we can see that sulfur weighs 256, so we use 256 grams per mole. Then we have heart of the problem, so we have moles of sulfur to moles of S2Cl2, so 1 and 4. Then our final conversion factor, we go back to grams of S2Cl2, and we get an answer of 67.3 grams of S2Cl2. Now we have to go back and do the exact same thing, but this time we'll start with our 71 grams of chlorine. So we did the first time with the 32 grams of sulfur, second time with 71 grams of chlorine, and go molar mass of chlorine, heart of the problem. You can see now we're going from chlorine, which is 4, to the sulfur S2Cl2, which is also 4, so it's a 4 to 4 ratio. And then we use our molar mass, so again this last part is the same. And this time we get an answer of 135. So we can see by this that the real answer, the true answer, is the 135. No, it isn't. The true answer is the 67, because that's the smaller of the two answers. And to answer the question, what is the limiting reactant? The limiting reactant is going to be the sulfur. Now they have the last part, and that is, what is the mass of the excess reactant remaining? So we can see that we have too much chlorine. Okay, then this is our limiting reactant. So the chlorine must be our excess reactant. So we want to know, well, how much of that is left over. So that means we have a third problem to do. And what we're going to say is, we're going to set up our given. Our given is our limiting reactant. And the desired is how many grams of chlorine. We're going to say, if we're going to use up all of our sulfur, how much chlorine do we get? So we start with 32 grams of sulfur, molar mass of sulfur. Heart of the problem, but this time it's between the sulfur and the chlorine, so it's a 1:4 ratio. And then finally we get grams of chlorine. Now with this we can find out that we have 35.37 grams of chlorine. That's what was used. So now our last job then is to find out, well, how much chlorine is left over. So that's kind of easy. We just say, well, we started off with 71.0 grams of chlorine, and we find out that we have used up 35.37. We'll round that up to 35.4 grams of chlorine. So what we have left over is 35.6 grams of chlorine. Now, a lot of times I see people try to use these answers here to somehow get this answer, and you can see they just do not add up. So this other answer, the 135, that is just not used for anything. So we have to go back and do a third problem, and the given is our limiting reactant, the desired is our excess reactant, find out how much you really do use, and then subtract from what you had, and that'll give you how much is left over. Okay, third kind of problem, a little bit easier than the others. This is the percent yield. And the percent yield is a situation where it says, suppose you have 1.203 grams of sodium, what's this called? Diborane, sodium diborane. And what happens is, you can start off with the reaction, take our given, and then we can just do a standard problem. And the question would be, well, how much B2H6, how much diborane would we get if we started with this sodium borohydrate? I'm not sure what that's called. So we can start with our 1.203 grams, use the molar mass, heart of the problem, 2:1 from the balanced equation, and then we get our molar mass of the diborane, and when we're done, we have an answer of 0.440 grams of B2H6. Well, the idea is, if everything went perfectly, that's how much of the B2H6 we would have, and we would name that as our theoretical yield. So theoretically, you ought to be able to get that 0.440 grams. But they tell us in the problem you only get 0.295 grams. So the percent yield is simply 0.295 divided by 0.440 times 100, and that comes out to be 67%. So for this reaction, it has a 67% yield. So notice the number that we actually calculated is officially our theoretical yield. In the problem, they tell us the actual yield, then we can calculate the percent yield. Last problem. Here's the disulfur dichloride. Okay, assume that you begin with 5.23 grams of SCl2 and plenty of NF. Okay, what's the theoretical yield of S2Cl2? And if 1.19 grams of S2Cl2 is obtained, what's the percent yield? So they're asking us first, just go ahead and solve the problem like you normally would. So if we had 5.23 grams of SCl2, molar mass to get the moles, the moles, heart of the problem, what we're trying to do is get from our SCl2 to S2Cl2, so we can see it's a 3:1 ratio. Then we go back to grams, so now theoretically we ought to have a yield of 2.28 grams of S2Cl2. Now, they tell us in the problem what we really have is 1.19 grams. So we take 1.19 grams divided by 2.28 grams, multiply by 100, and we get an answer of 52.2%. So that is our theoretical yield. That is our percent yield. We calculated theoretical yield, we were given the actual yield, and then we could calculate the percent yield. And those are the 6 problems.